Good evening.
Good evening, Doc.
Uh, it's 6 o'clock, so kindly remind your colleagues to join. Or the time is too early for them. In fact, if we are able to go the extra mile we did as at yesterday, what it means is that aromatic and heterocyclic is more than halfway through. And then we can also start something so that we might not even have to meet tomorrow evening. Then we'll wait and prepare for the weekend.
When I look for earpiece cover. Where are they? Hey, the fuck really did. Hello. Hello.
Please, good evening once again.
Good evening, Doc.
Good evening,
Right.
Doc.
So let's start something for today, and I think
Hello, sir, Doc.
we are to look at orientation of electrophilic substitution in naphthalene derivatives. So yesterday we did look at reactions of naphthalene, and we indicated that the position 1, which is the alpha position, is the most preferred site where an incoming group will go, because that is what will give us what the most stable product, because of the most stable intermediate carbonium ion. And aside the carbon 1 or the alpha carbon, the next site is also the beta carbon or the carbon 2. So we were looking at similarly how naphthalene, in terms of reaction, behave when we're looking at the nitration, the halogenation, the other reactions of benzene, which we already know. But if you recollect, when we were dealing with the reactions of benzene, we said if there is no group on benzene and you are performing any of the reactions of benzene, be it nitration, sulfonation, for the crafts, acylation or alkylation, the incoming group can go to any of the carbons on benzene, and it is the same product that you will get. But then when there is a group already sitting on benzene, then any of the reactions of benzene that you are performing, the existing group that is on benzene has an influence where the incoming group should go. So we were able to classify this group as electron donating groups and then electron withdrawing groups. We indicated that the electron donating groups, because they are pushing electrons to the ring system, they are said to be ring activators. They are activating groups. They make the ring more electron rich because they release electrons into the ring system. So they are what? Activating groups, ring activators. And for such groups, their influence on an incoming group is that they will direct it to the auto and para positions. So for an activators, for ring activators, for electron donating groups, they usually will give you two different products, the auto product and the para product. Then we did look at the other class of what groups, and we said they are the deactivating groups. Now the deactivating groups, because the aromatic nucleus is electron rich, they will tend to take away, remove some of the electron cloud to themselves, thereby reducing the electron density in the ring system. In so doing, they deactivate the ring. And when they deactivate the ring, then it means that their influence on an incoming group is to direct it to the methyl position. The methyl position. So this is just something for us to note when we're dealing with the benzene reactions. Examples of the activating groups. We had the hydroxy group, the alkoxy group, the alkyl group, the amino group. And then the deactivating groups, we know we had the carboxylic acid functional group, the aldehyde functional group, the cyanide, the nitro, and the others. These ones, we can always go back and then refresh our minds, because you need to be very conversant with these groups to be able to tell their effect on the ring, and for that matter, their influence on an incoming group. So with this idea, then we are also saying that when naphthalene has no group on it, and you are performing nitration, you are performing halogenation, it is the carbon 1, the alpha carbon, that the group will go always. But if there is a group on the naphthalene, then that group will have an influence on the incoming group. So here too, we have the ring activating groups, that's the electron releasing group, such as OH, OR, ACA, and the amino group. For these ones, they will tend to direct the incoming group to the same ring. Remember, naphthalene has 2 rings. So if the group is on one of the rings, then its influence is that it will have to direct the incoming group to the same ring that it is located. It will not direct it to the other ring. So an activating group in position 1 will direct an incoming group to position 4 as well as position 2. Now, when the incoming group goes to the position 4, that gives you the major product. And when it goes to the position 2, you have the minor product. I don't know whether any one of you want to ask how or why. And the reason is due to steric hindrance or steric effect. Because the existing group is on position 1. If it is directing another group adjacent to it, that's position 2, auto to it, what it means is that the 2 groups will be striving for the same space. And if the group is very huge, then it means that overcrowding, steric effect will lead to an increase in the internal energy of the molecule. And for that matter, because the internal energy is also increased, the molecule becomes unstable. And when the molecule is unstable, then you expect that that molecule will be formed in smaller amounts, even if it will be formed at all. But then, if it directs to the para position, you know, the para position to position 1, it just a perpendicular, it just opposite. So the 2 groups at the end of the day will be far apart. So the issue about steric hindrance, overcrowding, will not be present to affect the molecule's stability. And so that will give you the major product. Then the question is, if there's an activating group in position 2 instead of position 1, then you also expect that it will direct the incoming group to position 1. It will direct in this case, it will not direct it to any position 4, because the position 4 to the position 2 would have been on a different ring, the other ring. So when there's an activating group in position 2, automatically you are forming only one product, and that product will be when the incoming group goes to position 1. But when the activating group is on position 1, then there are 2 sides, the position 2 and then the position 4. When it goes to position 4, you form a major product. When it goes to position 2, you form a minor product. And that is for activating groups. That is for activating groups. So when you have naphthalene with an OH, the OH here is an activating group. So that is on position 1, as you can see. So if you are performing any reaction, whether it's nitration, halogenation, Friedel-Crafts alkylation, then this OH will direct that incoming group to its auto position here, that's position 2 or position 4. But you say that when the group comes to position 4, that gives you a major product. If it comes to position 2, that will give you what? A minor product. Just look at OH and then this whole group coming here. The nitrogen double bond, nitrogen with a benzene ring, very huge group. So if it is coming to the position 2, you expect that there will be steric effect or steric hindrance, which is brought about by overcrowding. The 2 groups will all be on the same side, and that would affect the stability of the product, and so to be formed in smaller amount. But if the second group comes to the para position, the position 4, you could see that the two groups are far apart, and for that matter, challenge of what? Steric hindrance, overcrowding will not be felt, and so the molecule becomes stable. And when it is stable, then it's going to be formed in large amounts. Here, the same OH on naphthalene, and you are performing nitration at this temperature. So it can come to position 2, that's the auto product, or it can come to position 4, that's the para product. Of course, the para product here will be the most stable, and that will be the major product because the two groups are far apart, while the auto product will be the minor product. Take note of the fact that the OH here, because it's an activating group, the incoming group is always directed to the same ring that the OH is bonded to. So the nitro comes to the same ring, whether it is the auto or the para. It does not direct to the second ring. It does not direct to the second ring. And in the last example here, because the group here is not on the position 1, but it's on position 2, then what we are saying is that it can only form one product, unlike this that we have the auto para. One product in the sense that the position 1 becomes an active site where it can direct the incoming group, that's the bromine 2. But if you look at this position 2, it cannot direct to this ring, okay? That is para to it. That would have been this carbon. But we are saying that all activators direct to the same ring. So this is auto to it, auto to it. This is meter to it. The para position will go to the other ring. So it means that will not be formed. So you get only the auto product here, which is the carbon 1. Of course, one will ask, why wouldn't it come to this side too? Because we have already talked about the reactivity or the active site of the naphthalene as the position 1 and position 2. Definitely, you expect that the incoming group, if the position 1 is free, it will come here because that is where you will get the most stable intermediate carbonium ion, which will make the final product also very stable. So this is for groups that are ring activators. They release electrons, they donate electrons, they make the ring more nucleophilic. So they direct an incoming group. If it's at position 1, it will direct it to position 2 or position 4. If it's at position 2, then it is only having only one site, which is position 1, that it can direct to. So it could be OH, it could be methyl group, it could be an alkoxy group, it could be an alkyl group, and other. So here you only need to go back, revise, and then be very conversant with most of the activating groups. Okay, so that you know that, oh, this one is an activating group, so it will direct to this or that. Then let's look at the deactivating groups. If the group on the naphthalene is not activating group, but then deactivating. An example of a deactivating group is a COH, that is the acid functional group here. For these ones, they direct an incoming group, okay, to the other ring. So if the acid COH is on this ring, then the incoming group cannot be on the same ring with it. It has to bring it towards the other ring. And it is preferably the position 5 or 8. And if you look at the position 5 or 8, it is this carbon here and then this carbon here. They are the ones which are closer or closest to the first ring. If you consider this as your first ring, okay, which carbons are closer to it? that is what we are trying to explain. Which carbons are closer to it? And you realize that it is this carbon and then this carbon. And this one, if you are to count from one here, 1, 2, 3, 4, 5. Carbon 5, 6, 7, 8, and carbon 8. So the incoming group can go to carbon 5 or carbon 8. Of course, for this deactivating groups, you will form only one product. And so if you look at the position of this and that one will be preferably formed, because then there wouldn't be any steric hindrance or steric effect as compared to you bringing the nitro here, which can lead to steric effect or steric hindrance. So self-assessment question here is write reaction equations. And please, I keep on saying, pay attention to all these self-assessment questions, because you see most of them in your exams in the same way as they are being captured here. So write reaction equations to show how you prepare the following compounds from naphthalene. So if you have naphthalene, how do you prepare 4-nitro 1-naphthalamine? Now, 1-naphthalamine means when you have naphthalene, there's an amino group on position 1, and then there's a nitro group on position 4. So if I start with naphthalene, how do I introduce NH2, an amino group? First of all, I'll do nitration. Nitration, that is nitric acid and sulfuric acid, will introduce NO2 to position 1. Now, when you get that one, you need to reduce the nitro group to NH2, to an amino group. And then here you can use thin in ACl, or you can use ammonium sulfide, in alkaline medium. These reagents are already known to you when we're dealing with the introduction to organic chemistry. They are used to reduce nitro groups to what? An amino group. Now, as soon as you reduce the nitro to an amino group, then you react again, you do another nitration. But because now the NH2 is an electron donating group, it will direct the next incoming group, which is the nitro group, to the carbon 4. And that will give you this first product here. So it will involve about two or three steps. Then we have 1,8-dinitronaphthalene. 1,8. So again, it also will go through 2 nitration stages. This one, when you perform the first nitration, you form the nitronaphthalene, you don't reduce it to NH2. Okay. Now the nitro group is a deactivating group. And because it's a deactivating group, it will not direct an incoming group to the same ring. It will direct it to the next ring. And the available positions are carbon 5 and carbon 8. So then it goes to carbon 8, and then you form your 1,8-dinitronaphthalene. If it goes to carbon 5, you form 1,5-dinitronaphthalene. Hello, Priscilla. Priscilla, you are giving us a feedback. All right. So I'm sure you are following. You have the materials already. I'm only throwing more light on it. I don't know whether this self-assessment question that I've just explained, but now you should pick a pen and a paper and then even try your hands on it. So I'm giving you just 2 minutes, okay? Or let's say 5 minutes. Let's do the A and let's do the B. Please, if we are all okay, we move on. If anyone has a challenge, we'll help the person. So I'm giving you 5 minutes to try your hands on it. Please, are we all through? I just want to know whether we've all been able to write the reaction equations to show how we start from naphthalene and get these two products. If anyone has a challenge, please let me know. Are we still working or we are okay?
No, Doc.
You are still working?
Yeah, Doc, please. Sorry, yesterday my network went off, so I couldn't stay through. So it's like I'm not able to catch up with
Please.
you as of
Yeah, so the lecture was recorded.
Yeah.
Who is your rep? Who is your leader? So that you can start calling for the recorded.
Okay.
And
Yeah,
then
yeah. Please, I'm the one. So I have to contact.
So please link up with the e-learning center, and I'm sure the way the lecture went, it's something that you can follow on your own. Okay.
All right.
Yeah.
Yeah. Okay. Okay, then. I'll do that.
All right.
Okay.
Do you want to continue later so that we move on? I should give you some later time. Please let me know. I'm taking my time here for a reason, so that you break my papers. So if you are having a challenge with these two exercise here on the self-assessment questions showing here, please let me know.
Yes, Doc, we're having challenge.
Please, what's your problem? Do you know the structure of naphthalene?
Yes, please.
So please draw the structure of naphthalene. When you are done, let me know.
Okay, I've done that.
You've done that. Okay. So now we have naphthalene, and we want to prepare the A, 4-nitro-1-naphthalamine. Okay. So
Okay, sir.
what I will ask you is that, we have done the nomenclature. You understand how to name it. So try and see if you can get the structure of 4-nitro-1-naphthalamine. Try and see if you can draw that structure.
Okay. Oh, nitro.
Casey, were you able to do it? What about the gentleman who?
Hello, Doc.
Yes. I asked you to draw the structure. Have you been able to do it?
Yes, Doc.
Okay. So now, to move from naphthalene to that final product, that is the 4-nitro 1-naphthalamine. Okay. There are reactions that you need to perform. So when naphthalene is there, okay, we can introduce a nitro group. So we perform nitration. Now in nitration, you need what? Nitric acid in sulfuric acid. So you just show an arrow, and then you bring HNO3/H2SO4. And that will mean you are introducing a nitro group, NO2, at the position 1 of naphthalene. And I'm sure you know position 1. So put nitro NO2 group on position 1. And that will be nitro naphthalene or 1-nitro naphthalene. Please do that, and then quickly let's move on.
Okay, I've done that.
Okay, so now that nitro group on the naphthalene, the question you ask yourself is it a ring activating or deactivating? Okay, if it is a ring deactivating, of course, nitro group is a deactivating group. Then there's no way you can have another group coming to the same ring that the nitro group is. It will rather push it to the next ring. Is that right? So it means you have to find something to do to the nitro group. And because the final product, we have an amino group, NH2, how do we convert NO2, nitro, to NH2, amino? And that one is a reduction reaction. So you can use thin in ACl or ammonium sulfate, in alkaline medium. So thin is SN/ACl, that's the reagent, or you can use the NH4 into bracket 2SO4 in alkaline medium. This one will convert the NO2 to NH2, and that will be what is disturbing the class today. We didn't experience this. We didn't experience this yesterday. So you get the NO2, which was on the position 1, now being changed or reduced to what? NH2, from NO2 to what? NH2. And that NH2, which is the amino group, is an electron donating group. So it activates the ring. So that one can direct any incoming group to the same ring. And from the product that you wrote, you could see that after writing the naphthalene, you have NH2 and then NO2 on the same ring. So it means that if the NH2 can bring another group to the same ring it is, then we also know that the ring activators, they direct towards the position 2 or position 4. But we see that the position 2 is a minor product, but then the position 4 is what? A major product because of what? Absence of steric hindrance. So it means we have to do another what? Nitration. HNO3/H2SO4. And when we do this nitration, the incoming nitro group will go to what? The 4th position. That's para to the NH2. And that is the final product. The name has been given as what? 4-nitro 1-naphthalamine. So we'll write that one. And I've written something here. So I'm sharing to you on your WhatsApp platform so that you probably will see what I've also done and compare with yours. Okay.
Okay, Doc.
Yes.
Okay, sir.
All right. So I've sent it, and you can all check how I show the arrow movement from the naphthalene. I did nitration, then I got the nitro naphthalene. I reduce it, and then I got the amino naphthalene. Then I did another nitration, and then I got the nitro group being on the same ring as the NH2. So this is how I would, in an exams, expect you to present using equations. And if it is 10 marks, you get all.
Hello, Doc.
Yes.
Doc, is the reagent used on the nitration, are they catalysts?
The what?
The reagent, example, the nitric acid. That's when we're changing the
So
4-nit.
So from your previous knowledge in Introduction to Organic Chemistry, there's semester 1. Okay, reactions of benzene. We consider 5 reactions. One of them was nitration.
Okay.
And nitration is putting a
Okay.
nitro group, NO2, on benzene. And the reagent is HNO3/H2SO4. Nitric acid is sulfuric acid.
Okay.
So I expect that
Okay.
this reagent, by now, you guys should be very conversant with them. You see, all the reactions of benzene is what we are applying to other organic aromatic compounds. So let's
Okay.
try and then maybe get back and then revise some of these things. So it's
Okay.
a reagent. Yes.
Thank you, Doc.
And
Okay.
the one that is used to reduce the nitro group, the one that is used to reduce the nitro group to an amino group 2. You see, I've given 2 there. I think there are 3. You can use iron in ACl or tin in ACl or the ammonium sulfate alkalines form. Any other question, please, based on what I've shared there? You are all okay?
But
So can
yes,
we do
Doc. Yeah, I
can
think
we do
I'm.
the second one? Can we do the second one?
Okay, we can try. Yeah.
Yes.
Mm.
So my advice is that in a question like this, you have been given the starting material and the product. So you have to write the starting material, the structure down, then the product, and then you work towards it. That's why we started with it's not always that I will give you the structure to name it. Sometimes I can give you the name, as you can see here, and ask you to draw the structure too. So take note of that.
Hello, Doc.
Yes.
Doc, please, for the second one, are we going to use the same reagent?
So
The 1A2.
So what I want to also know from you is that, have you written the starting material naphthalene down? Have you written the structure of the 1,8 dinitro naphthalene down?
Yes,
If you have done that, then you know that from the starting material to the product, you are only introducing what? Nitro group, NO2, isn't it? And what reagent do we use to introduce NO2? It's the same nitric acid and sulfuric acid.
Okay. Thank you, Doc.
So I've sent the second one to on your page. And so if you have seen it, compare with what you have done, and then let's move on. So please, if you see these two in your end of semester exams, don't be panicked and don't get it wrong. But then just to get the understanding is what is important, because there will be other and similar questions to this. So try to get understanding, please. So now we've looked at naphthalene. So we want to pick another fused aromatic compound, which is the anthracene and then the phenanthrene. And yesterday we realized that these are all three aromatic rings fused, three benzene rings fused, the anthracene and then the phenanthrene. The difference is that the anthracene, the fusion is done and it's linear, whilst the phenanthrene is not. So the sources, they are normally obtained from fractional distillation of coal tar. The same thing applies to the naphthalene. So naphthalene, anthracene, phenanthrene, the source is from distillation of what? Coal tar. Anthracene oil fraction is cooled and pressed to obtain the solid crystals out from the liquid. The pure anthracene is purified by sublimation. The crude form contains phenanthrene and carbazole. Okay, so please, if you are talking about the crude form, then these two components are always there. That is, if you take anthracene, you will get traces of what? Phenanthrene, and then traces of what? Carbazole. And so how to purify it is by sublimation, and that will leave behind the phenanthrene, and then the carbazole. The solid is powdered and washed with naphthalene solvent, which dissolves the phenanthrene, and the remaining solid washed with pyridine, which dissolves the carbazole. So you see, in getting your pure anthracene, you need naphthalene solvent, which you have to add, and that will dissolve any traces of phenanthrene that is found in the anthracene. And then you go ahead and wash again the anthracene with pyridine, which again will also dissolve any traces of what? Carbazole. So if you are asked in a purification of what? Anthracene, describe the purification of anthracene, everything is as captured here to get pure anthracene. So we are going to look at the structure and nomenclature of anthracene and phenanthrene. So addition of a third benzene ring to naphthalene molecule by linear or angular fusion. So if it is linear, then we have anthracene. If it's angular addition, then we get what? Phenanthrene. Now the phenanthrene can assume these two shapes. They are the same. Either this one, okay, or this one. And then this is the anthracene. Now already there's some numbering system here. And like we saw in the numbering of the naphthalene, okay, where we start from the carbon 1 number either clockwise or anti-clockwise, same way the numbering of anthracene is also starting from carbon 1 here. And when we start from here, you go clockwise. So 1, 2, 3, 4. Okay. Then you leave the middle ring. Please look at the numbering well. 1, 2. So there are two extreme rings, and then there's one in the middle. So if you pick, let's say the one at the extreme right, and you start your numbering 1, 2, 3, 4, and you are done, you skip the middle ring and go and continue 5, 6, 7, 8 on the other extreme ring on the left. When you are done numbering the two extreme rings, before you come to the middle one, and the two carbons there, assume 9 and 10. 9 and 10. That is the numbering of anthracene. So please look at it. Look at it. Then that of the phenanthrene, again, you could see that the three rings, there are two which are at the extreme ends, and then there's a middle one. So when you start from the far left, that is this one, 1, 2, 3, 4. You leave the middle one, then you continue from 5, 6, 7, 8. Then you come to the middle one, and then you have 9, 10. And then the same thing applies to this one. So please pay attention to the numbering system of naphthalene, the numbering system of anthracene, and then the numbering system of what? Phenanthrene. Because when it comes to naming of their derivatives, these numbers will let you know the position of the substituent groups. And then you can use the positions accurately. Are you okay? Can we move on?
Yes, Doc.
All right. So here we are, and I've given you some derivatives of what? Anthracene and then phenanthrene. So if you are really conversant with the numbering system, then you could take note of the fact that the first one here, there's a meter on position 1, there's another meter on position 2. So if you want to name it, it becomes 1,2-diameter anthracene. 1,2-diameter anthracene. If you look at the second one, the numbering system starts from here: 1, 2, 3, 4, 5, 6, 7, 8, then 9 and 10. Now you could see that there are two substituent, bromine substituent on position 9 and 10. So if you are naming it, you name substituent first. So that would be what? 9,10 dibromo anthracene. Now if you look at the third one, the numbering system starts from here. So the bromine here will be 2, this will be 3, this will be 4, 5, 6, 7, 8. And then because you see here, we say 9 and 10. But if the substituent is on the down one, then that one becomes 9. If the meter here were to be at the top, then that one becomes the 9. If the 2 all has substituent, then one becomes 9 and one becomes 10. So here, after numbering up to 8, we will give the 9, position 9 to where the meter group is. And then the 10 will be the up here. So that will be 2-bromo 9-meter anthracene. And then the same thing, if you are very conversant with the numbering of the phenanthrene, then you know that these ones are 4-10 diameter phenanthrene. And this one will be 9-chloro 10-nitro phenanthrene. So what is key here is the structure of anthracene, the structure of what? Phenanthrene, and then the numbering system, which I show you here. We need to be very conversant because you will need these numbers to know the position of the substituent groups. Yes.
Yeah, please. I think that one can also decide to start the numbering from the left side.
You mean which one? Is it the anthracene or the?
The anthracene.
You want to start the number from here?
Yes.
Now, if you start from here,
that also be right?
It will not be right because IUPAC has a general rule that says that always choose the path, the direction that will give you the least sum of the substituent positions. So if we go this way, as you are proposing, then it means we can only go anti-clockwise. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we are going to have 7, 8 diameter anthracene. Now 7, 8, and 1, 2. Which one is giving the least position to the substituent? It's 1, 2.
Yes, 1, 2. Okay. Okay, Doc. But so if the substituent were to be at the left, will it be right to also start?
Yes.
The
Yes. If the one of the meter were to be here and the other one were here, then definitely the numbering will not start from here. It will start from this side.
Okay, Doc. Yeah. Okay, Doc. Yeah. Thank you.
Welcome. Yes, John.
Thank you, Doc. Can we apply that to the phenanthrene?
Yes.
The first diagram where we have the meter group. Can we make that one 1 so that we will rather go anti-clockwise?
No, you see, the numbering of phenanthrene had already been established for you. Okay. So the 1 is always here. Okay. then you go 2, 3, 4, 5, 6, 7, 8, then you come 9, 10. Or you can start the one from here. You see, this one was going what clockwise.
Yes.
Or you can start from here and then you go what anti-clockwise. So the number can only start from the two extreme ends. Okay, it can start, the one can start from here and then you go clockwise, or you can start from here and go anti-clockwise. But the question is, in which of them will you get the least position for the substituent? And that's the most appropriate one.
Okay.
I will do well. Like I said, this course is not much in terms of the volume, and so maybe when I think I have done enough, and even we are not exhausted all our meeting times, what I will use that time to do is to maybe use my chem draw and then give you more examples, okay, different ways. Then you try your hands on, but get the foundation, okay. All right, so these are all nomenclatures, and I think you should be okay. Now we know benzene, okay, which is one what do you call it, neutral homoaromatic compound. We said it has two canonical forms, two resonance structures, right? That's the CHE425D. And then a mixture or a hybrid of the two is what we call the resonance hybrid structure. So when we take anthracene and then we take phenanthrene, they can also show different canonical forms, different resonance structures. And then the different canonical or resonance structures is just about movement of the pi bonds in the ring. Okay. So here you could see that look at there's a double bond here, double bond here, double bond here. Okay. So when you push this one here, this one will go here and this one will come here, and that will give you the middle one. Okay. And then you keep on alternating so that at least every time you shift one double bond, it means that the others will also be moving. So we are saying that when you do this kind of resonance, stabilization structures of anthracene, you are getting 1, 2, 3, 4 different forms. You are getting 4 different structures. Okay, and the 4 structures, a hybrid of the 4 is what represents the true structure of anthracene. Then in the case of the phenanthrene, we have 1, 2, 3, 4, 5. Okay, now when we talk about the stability of aromatic compounds, one of the points is that the more canonical forms you have, the more resonance structures you have, the more stable you are. So if you are talking about stability of anthracene and phenanthrene, we can say that phenanthrene is more stable than anthracene. And you can look at the resonance energy, 92 kilocalories per mole, whilst the anthracene is 84 kilocalories per mole. So you realize that the resonance energy here tells you that the phenanthrene is more stable than the anthracene. And the stability we are saying is linked to the number of canonical forms a molecule. So if a molecule can represent itself, can exist in different canonical forms, the more the forms, the more stable it is. Yes, Antwi.
Thank you, Doc. Doc, please, the resonance. How is it moved from the benzene ring? The movement, how is it done?
Currently, what you see is not benzene ring. I'm only telling you that when we started with this lecture, and then I was talking about the structure of benzene, the CHE425D structure. I show you 2 different forms.
Yes.
That when
Yes.
you see the double bond and the single bond should always alternate. There should not be two double bonds on adjacent carbons. So when a double bond comes, there should be a single bond, double bond, single bond, and that's what we mean by one of the conditions that classify a compound to be aromatic. It should be what? Fully conjugated. Okay, meaning you should have a double bond alternating with what? A single bond. Do you understand? Such that all the carbon atoms will be what? sp2 or sp hybridized. So here too, if you accept the first structure, of anthracene here, you just identify the position of all the double bonds in it. All you want to do is, let me shift, this double bond here. I hope you can see my arrow. Can you see my arrow? Okay, let this one. You can see my arrow, this one. Now let me shift this double bond down here to this side. When I do that, it means that the one at the top here cannot be there because the two double bond cannot be adjacent. So it means when I bring the one down here, then this one also will shift here. Then this one also will shift down here. And that's what you can see in the first ring here. Okay. And that makes this one different from this one. Then when you continue, you get different arrangements of the double bond. Okay. If you look at the fourth one and the third one, you see this one, there's a double bond here. But over here, there's no double bond here. So for me, if in an exams, I ask you to show the canonical structures of anthracene, first of all, you can draw the three rings, four of them, fuse. Then you will be positioning the double bond still with you'll be getting different what arrangement. Okay. And so these different canonical forms is in line with what is stability. So the more a molecule can express itself in different canonical forms, in different resonance structures, then the more stable it is. So we are comparing these two, though they are all made up of three fused benzene rings. The anthracene can only form 4 canonical forms or structures. The phenanthrene is giving us what? 5. So then automatically, this one having more canonical structures means it's going to be more stable than this. And that's what you can see their resonance energy as measured. This one is 92 kilocalories, and this one is what? 84 kilocalories. So all the information I've said, yes. I was going to say that. I was going to say that all the explanation I've given to you, is captured on this slide. Comparison of the stability between anthracene and phenanthrene. If you can take your time and read, you could see that all that I've said is what has been summarized here. So take your time and read yourself.
Okay. Thank you, sir.
Welcome.
Hello. No, hello, Doc.
Yes.
Doc, my question is for anthracene and then this and the phenanthrene. Both of them have three benzene structures. Both of them. But I think for the phenanthrene, I think that one, the arrangement of the structures was different from that of the anthracene.
So earlier on, I showed you a slide where we were comparing the two, and we said the two of them are all having 3 fused benzene rings. Just that in anthracene, the fusion is linear. The third one is linear, okay? Whilst in the case of phenanthrene, it is in what? Angular shape. Now, anthracene and phenanthrene are said to be isomers. If you can check the number of carbons, the number of hydrogens, they are the same. It's just the structural outlook that the third ring of anthracene is linear, but that of the phenanthrene is what? Angular. And that structural differences is what is bringing about differences in their stability, and then is being explained by the number of what resonance structures that they do form.
So I think you mentioned a term. You mentioned a term. You said you mentioned a term just right now. But I've forgotten about this in the way
that they are isomers.
Isomers. Oh, okay.
Yeah, they are isomers. Isomers have the same molecular formula but different structures.
Yeah.
So if you check the number of carbons in anthracene and phenanthrene, you get the total number of carbons to be the same. Their number of hydrogens to be the same, but their structure, which we are saying that the third ring in anthracene is linear to the naphthalene, but then it is angular to the naphthalene in the case of phenanthrene. So,
hello, Doc.
Yes.
Doc, you said the more something, the more stable it is. I didn't
So
get
I was
that
saying
word.
that
when we're talking about the anthracene.
Okay, so let me build it from benzene. You know, when we're talking about aromatic compound, we said they are very stable. That's why they don't undergo addition reactions. Rather, they undergo what? Electrophilic aromatic substitution. So we are still trying to explain what are the key features that makes aromatic compounds stable. So we said that benzene, the kekulé structure, can exist in two different forms. Okay. And the two different forms is what we call the canonical forms or the resonance structures. And benzene has two. Now, for the other compounds or any other organic compound, if a compound has more canonical forms, if a compound has more resonance structures, okay, it does corresponds to its stability, in that the more canonical structures you have, or the more resonance structures a compound has, the more stable it is. Okay, it's like you are able to, the same compound, but you are able to adapt and then change it to different forms or structures. Okay, and you are saying that the more a compound is able to do that, the more stable it is. So if you have three compounds, one has two resonance structures, one has four resonance structures, one has five resonance structures, and you want you to arrange them in terms of stability, then the one that has five resonance structures will be the most stable, followed by the one that has four, and then the one that has two will be the least stable. Does that make sense?
Okay, Doc. Yes,
so look at the first question here. Phenanthrene and anthracene, which is more stable? Explain. So the explanation is here. Stability is associated with what? Resonance structures. So first of all, you say that phenanthrene will be more stable than what? Anthracene. Then you go ahead and say that stability is associated with what? Resonance structures. Whilst phenanthrene has what? 5 resonance structures. Anthracene has what? 4. Do you understand? And there are other information captured here which you can add it to your explanation. Then state reasons that account for aromaticity of anthracene.
Okay,
this one too is there. Provide the IUPAC names for the following compounds. I think we have looked at some. Do you want to try the ones here, A, B, C? Or I should let you go and do it on your own?
Please,
Go and
Doc,
try your
we are
hands.
trying. We are trying, yeah.
It's not everything that we have to try here. Some of them you have to go and work on your own so that we move.
Oh, but this is one day we should be able to try it.
All right.
I'm on the
Hello, please, Doc.
Yes.
The first, yeah, the first one, the A. I named it. I named it as 10 chloro. Sorry, 9 chloro, 10 methyl anthracene.
Yes, you are right.
Yeah,
You are right.
yes.
And
Yes,
the
sir.
reason why you gave 9 to the chloro and then
Yeah.
the 10 to the methyl is that when you were
Yeah.
naming, you brought the inorganic first.
Yes.
So if the inorganic
Yes.
will come first, then that one should be given the list number. Good.
Yes, yes, sir. Yes, sir.
So you
Thank
see,
you,
this whole thing, I don't know, but if you follow the rules, this course, it's not difficult. You can easily, so I think it's a good attempt. Is anyone taking the second, the B and the C?
Hello, Doc. Doc.
Yes.
The B.
Yes.
Is let me come back again.
Yes.
Doc. The B is 9,10 ozo. Phenanthrine. 9,10.
No. You should be very conversant with your substituent names. In fact, we've been doing naming since introduction to organic chemistry, organic substituent, inorganic substituent. So you should be very conversant with them. The substituent groups there are not oxo. They are not oxo.
Doc, yeah. It's I know. Doc, it's 9,10 diol phenanthrine.
No.
9,10 diol.
No. Now tell me the substituent over there. How do you mention that substituent? Because you are not naming it as an alcohol. You are naming it as what? An aromatic compound. So the OH is a substituent. How do you name OH as a substituent? We know methyl, you know ethyl, you know propyl, you know chloro, you know bromo, you know nitro, you know cyano. So these ones, how do you name the OH there as a substituent? That is the only challenge you are having in terms of their name. Yes, any other person? Okay, so this one is 9,10 dihydroxyphenanthrine. 9,10 dihydroxyphenanthrine. Of course, when it is an alcohol, that's what we say is all pentanol, methanol. But if it's an alcohol and it's a substituent, And OH is what? Hydroxyl. The substituent name is what? Hydroxy. So if there are two of them, dihydroxy. So 9,10 dihydroxyphenanthrene. Can we take the third one?
Hello, Doc.
Yes.
2-chloro-10-nitrophenanthrene. 10-nitrophenanthrene. Hello, Doc.
Yes.
Doc, I said 2-chloro.
Yes, you are right. You are right.
Okay.
You are right.
Thank you, Doc.
So now, methods of preparing anthracene. How do we synthesize them? And we can use the Friedel-Crafts acylation. So here you don't begin with benzene. You can begin with begin with phthalic anhydride and benzene, then Eloise acid. Then you form this intermediate. Then you perform what we call cyclization. Then when you form the cyclization product, which is a 9,10 anthraquinone, then how do you reduce these ones and then aromatize them? Middle ring is the use of what? Zinc in alkaline medium, and then you form your anthracene. So know the steps for the synthesis of what? Anthracene. Then
Frimpong, please mute your mic. Frimpong.
Yeah, Frimpong.
Then
Please.
there's a second method, which is the cycloaddition reaction. Okay, that is just having two diene. Okay, this is a diene, this is a diene, and then you have a 1,4 dione. So they form what we call diaster addition, and you get this. Then of course you need to find a way of what? Aromatizing the two rings. And so you can do that with what? A base in oxygen or chromic acid in what? Acetic acid. And then when you form this, hold on. When you form this, then how then do you also reduce this ketone functional group and then aromatize this? So at this point, the truth is that the more you look at it and look at the reagents and where they appear, the better. In some cases, I will show you the trend, the step by step, and I will leave the reagent out and you will supply them. Or I'll be bringing the reagent and you'll be producing the intermediate products to the final one. Or you can be asked, pick any method. The first one I've shown you, this is a second method of preparing anthracene. So the one that you are comfortable with, you can then use. Okay. Then there's a third one. This is a third method, that's the F synthesis. The F synthesis is a condensation reaction, okay, where you are giving a polynuclear hydrocarbon through pyrolysis. You then will form your anthracene. And this one is just a one step. So you can see that this one is very simple, okay? And then you form your anthracene. So please, all that I'm saying is that from here, I won't waste time. Different methods for preparing anthracene, okay? That is what I have just outlined them. So this is another one. That is preparing anthracene from benzyl chloride. It's also a two-step reaction. So the point is that there are a number of methods, but at least as far as this course is concerned, just at least one of them, you should be conversant with one of them, okay? And then the others that are also following are, if you know one of them, then the preparation of the derivatives is also not a big deal, because then the benzene that you are going to use, whatever derivative that is there should be attached to the benzene nucleus, and then you proceed. So that should also not be a problem with the derivatives synthesis. It's the same method, just that the starting material have to bear your group of what substituent. You have self-assessment question here. Then my advice is that I did all this so that at least once you learn my slides, at least you also be trying your hands on these questions, and then you should be okay going forward. Then the synthesis of phenanthrene to that one, we have a number of methods. So here you also pick the one that you are conversant with, and then you master it. There are a number of them. You need to have an idea of all of them, but at least as far as the course is concerned, you should be able to pick out one. So preparation of phenanthrenes from naphthalenes involves series of steps, including Friedel-Crafts, acylation, and then 2 Clemmensen or Wolff-Kishner reductions. We have seen Clemmensen reduction before, and that is zinc in mercury in ACl. That's Clemmensen reagent. Wolff-Kishner reduction, you have hydrazine in alkaline medium. So these two are used to reduce a ketone functional group to what? A methylene group, CH2. Then we have the Haworth, succinic anhydride synthesis, which also start from naphthalene. Then we also have the substituted phenanthrene synthesis. So here, the ones that I've mentioned, that is how you get them. Okay, that is how you get your phenanthrene synthesized. So you try to be very conversant with one of them. This is just a one-step synthesis of what? A derivative of phenanthrene, just one step. So you have this starting material in alkyl lithium, then acid hydrolysis, you heat, and then you have what? An ethyl phenanthrene, So this another method, the Badan-Segumta phenanthrene synthesis. Some of the names, they are named after those who really develop those methods. So there are a number of them. And even beyond this course, there are other methods, we've not even mentioned them here. But what we are to do is not to bother you with all the numerous methods of preparing anthracene or phenanthrene. But what is key is that at least you should be able to pick a method that on your own, let's say if you want to say you want to prepare such a product in the lab, you can easily do that. We have the Shaw synthesis, which is also here. So the different types of methods, please, you have the slide, so you should try and then be going through them. Then we saw the reactions of naphthalene. So let's also look at the reactions of anthracene and phenanthrene. Both phenanthrene and anthracene are less resistant towards oxidation or reduction than naphthalene. Can somebody explain this to me? The first statement. They are less resistant towards oxidation. We saw oxidation and reduction in naphthalene, where the different temperatures was causing either all the double bonds in the ring to be reduced or some. We saw the oxidation aspect too. Now we are comparing naphthalene to anthracene and we are comparing naphthalene to anthracene and phenanthrene, and we say that the phenanthrene and anthracene, they are less resistant towards oxidation. All right, let's think about it. Then the reaction occurs at 9 and 10 position. So for both anthracene and the phenanthrene, the position 9 and 10. That is where all the reactions takes place, okay? That's where all the reaction takes place, whether it is oxidation or reduction. So some of the examples are here. You could see that this is anthracene. And the reagent here is what? Oxidizing reagent. So it's oxidation. So when you oxidize anthracene, you realize that the position 9 and 10 are oxidized to this what? ketone functional group. So you get what? 9,10 anthraquinone. Okay. The same way when you reduce 9,10 anthraquinone, you also get what? Anthracene. Now, if you have phenanthrene and you oxidize, it's still the 9,10 positions that you form your ketone functional group. So that is where the reactions takes place. And then the reduction reaction 2, when you reduce anthracene, it is the position 9 and 10 that get reduced. Okay, so that they cease to be aromatic. It is the position 9 and 10 that reduce. So the double bond there reduces, and then you then have an sp3 hybridized carbon atom, meaning this is no more aromatic because the system is not fully conjugated. All the carbon atoms here are not sp2 hybridized. You now have an sp3 here, sp3 here, sp3 here, sp3 here. So then it cannot be said to be what? Aromatic again. So more examples of reduction reactions. And we have bromination, okay, where you are introducing bromine. If it is just one, then you use a bromine in Lewis acid. If it is to form a dibromo compound, then it's like the alkene, okay, doing bromination in alkene. So bromine carbon 10, then that will reduce the position 9 and 10 double bond so that you get a dibromo compound here. Okay, the same thing applies here and then here. So take note of the different reagents and conditions and then the expected product. More examples of reactions of anthracene and phenanthrene. Then nitration. I mean, nitration is one common reaction that happens. So you could see, look at the two different, if you use aqueous nitric acid, you form 9,10 anthraquinone. But if you use aqueous nitric acid under this condition, then you form what? A dinitro or a mononitro what? Anthracene. Okay. So look at, so here you form a mixture of the two, but we are saying that at an extreme temperature of 295, you form the dinitro. If it is halfway, that's 145, you only form what? A nitro anthracene. Sulfonation. So again, all that we are doing here is the already known reactions of benzene that we are aware is the same reaction that we want to see how other aromatic compounds also behave. So sulfonation, if you are doing sulfonation, the carbon 1 of anthracene here is what you get, it gets sulfonated, or the carbon 2. And the reasons are captured over here because the carbon 1, I mean, at room temperature gets sulfonated, but at an elevated temperature, then it is the carbon 2 that gets sulfonated. Okay. All right, so we will be ending soon. The Dallas-Dow reaction, you know, I taught you organic reaction mechanism, right?
Yes, please.
Yes,
Yes,
Doc.
Doc.
Unfortunately,
Yes, Doc.
that one was so voluminous that the photochemistry aspect of it, which we would have had this as that reaction, we couldn't reach there. Okay, so this is one of the reactions that can also take place in anthracene. Don't worry yourself with that one too much. Then ozonolysis. Ozonolysis, that's oxidation followed by using peroxyacetic acid. And then you form, if you use ozone, you form a diol, that's 2 aldehydes. But you know, aldehydes too are further oxidized what? Acid. So if you use a strong oxidizing reagent, then you form a diacid. But if it is just ozonolysis, you form a dialdehyde. Okay. So this one is a strong acid, so you form the diacid straight. Hydrogenation, just add, I mean, you are just adding hydroxy group, okay? So the hydrogenation of phenanthrene leads to the formation of 1, 2, 3, 4, 9 phenanthrols. So the position 1, position 2, 3, 4, 9 all get substituted with what? The hydroxy group, as you can see. And that is that for today. Self-assessment questions are here. And the next time we meet, please take note of this and then remind me. The next time we meet, we have looked at benzene, just one benzene nucleus. Then we look at naphthalene, 2 benzene fuse. Then we look at anthracene, 3 benzene fuse linearly. Then we look at phenanthrene, 3 benzene ring fused in an angular form. So beyond the 3, we are looking at what? Poly. Poly means many. So there are some other aromatic compounds in which you have more than what? 3 rings fused. We call them the PHs, polycyclic aromatic hydrocarbons. There should be N here. Yes. Polycyclic aromatic hydrocarbons. So our next meeting, or you want us to continue?
Doc, we are tired.
Should we do 1 more hour?
Doc, we are
Please
tired.
no, please no.
We are
Let's
tired.
end here.
So, all right. So please, we've done well. Basically, like I'm telling you, as far as this course is concerned, okay, we are more than halfway through. So the materials left for us to cover after the pHs is just the heterocyclic compounds, which you also have to know the different classes, how to name them, and then their synthesis and some reactions. And then that will be summarizing everything under aromatic and heterocyclic chemistry. So we have done well. We've gone more than halfway, beginning like this. So I suspect that over the weekend, we are not meeting tomorrow. We are not meeting tomorrow as initially we scheduled. So you have tomorrow to yourself to revise what we have done on the aromatic and heterocyclic. Tomorrow, because we are not meeting, I will start sharing materials on the natural products chemistry too. So that you start, that one is basically about reading. You start looking at it. And then over the weekend, this particular weekend, I am available for us to have our normal lecture period meetings. Okay. I think 7 to 11 and then 11:15 to, all right. So when we are able to do those 4 hours, hey, we'll go far. But then if I'm moving too fast, please slow me down. The fact that we want to cover everything and finish everything, you also need to understand certain basic things, okay? So we will end here for today, and then we will continue Saturday in the course of the day. If there's no other question, please, from where we've gotten to, I expect that you should go back and start answering the review questions or the tutorial questions I gave. Some of them, you should be able to answer them now. Start solving all of them. Then the self-assessment questions too. It will be very, very helpful for you. Yes.
The review question, the theory aspect, you gave us just two questions.
Oh, so you want more? I thought you said you are tired.
You want more? The theory, the review.
You see, you
want more.
You see, Ghana man. If you give more,
that part there. You want more.
If you give more, problem. If you give less, problem.
Oh, that part, dog. We want more. The review.
Hello, Doc.
So I like I said,
Hello?
I indicated earlier on, the way we are moving will mean that in our subsequent meetings, we are likely to even not do so much. So I will use the other time to get you more examples to be try your hands on. Is that okay?
Okay, Doc.
All right.
Yes,
Please,
Doc.
are some
Hello,
of you
Doc.
doing
Hello,
some
Doc.
of you doing stereochemistry? Are some of you doing stereochemistry?
That one is pure physics students. The
Oh,
pure physics.
okay. All
Because we've
right.
done it already. Read the
Yeah,
chemistry.
you I know the chemistry major you did it, but when we were doing it, they should have joined, but I'm told they didn't, and so they are now going to do it. So if those here you are not part, that's okay. At least
But Doc,
I'll,
it's part of our registered courses. So
Also,
but
read the
but the previous one, have they published the results?
the stereochemistry has come out.
Yes, Doc.
Not, they have released
Yes.
it for a long time.
That one, the results is published, right?
Yes, Doc.
Yes, Doc.
And then it has been registered again.
Yes.
Doc.
Okay, so this one will be deleted, okay?
Okay.
But for the physics people who didn't do it, it will stay.
Okay.
Okay.
I hope, Frimpong, I hope you remember when this issue came up, some of the people were saying that they couldn't register stereochemistry.
Yes.
And then you wanted me to take some steps on it. Yeah. So I think that's what they are trying to resolve. Yeah.
Doc, I can't remember the last Wednesday or Thursday. I asked you a question about the practical. The practical
Yes.
on
Yes.
the physical chemistry and that.
We have Chem 310 and Chem 319. These two practicals is what is left for you, chemistry major students.
Yes, Doc.
One of them is organic and one of them is physical inorganic.
Organic, yeah.
I will handle the organic. I'm coordinating the organic, and then Dr. Betofori will coordinate the physical inorganic. But what we are saying is that after we are done with our online engagement, there will be 1 weekend for practicals. So that weekend, you all will go to your respective centers, and we will pick, let's say, Saturday for maybe the organic, and then we'll pick maybe the Sunday for the physical inorganic. And you are done for the program. So I will start sharing the organic practical manual, this thing with you, the practical manual, okay, that you'll be using in your respective lab. I will share a soft copy on your page, and I'll tell Dr. Betofori to do the same for the physical.
Okay. Doc.
Yes.
Doc.
Hello, Doc.
Doc, please, I'll be very glad if you can instruct the code people to upload the videos for us early.
Hey, who am I to go and instruct them? I can't instruct them. Me deep power hole.
Because some of us, we have to go back and listen to the recordings again.
You the students are more powerful, okay? You are our customers. Do you understand?
Okay.
Thank you. You are our customers. So we have to do what you like so that we get more customers. So
Doc,
who is the rep?
The set.
Please, Doc, I'm here.
Set. So I even told Set to link up with the e-learning unit. Of course, I can tell them, but mostly we know they are student friendly. When you get to them, they will attend to you. Okay.
Yes.
You see today. You see today like this, it's a makeup lecture, but then they are recording for us. Okay.
Yes.
It's a makeup lecture, but then they are here recording for us.
Yes.
So please, they will release it, and when they release it, and then you take your time and you follow the way the lecture went, questions that came. In fact, you should be okay.
Yeah.
All right.
So hello, Doc.
Hello, Doc.
Was yesterday's lectures recorded?
Yes, yesterday's one was recorded, please.
Okay, so we can get to submit it.
Yes, please.
Okay, thank you.
All right. Thank you very much for coming and have a good night. See you over the weekend.
Are you taking our juniors on the chemistry?
The cohort 3. Hello? Hello?
Dog, he says, are you taking the cohort learners?
Oh, that one they
Yes,
say.
yes. In fact, so now let me chip in this. You know, they are also begin this weekend. And I have a class. I think there's going to be a class.
Yes.
I'm taking them introduction to organic chemistry. So please, Frimpong, give me a reminder, okay, to check my schedule when they have their class. Then I have to find a way of rescheduling one of them.
But Doc, I don't have their timetable. So how would I know that you've
No, I mean, give me a reminder. Remind me to check my schedule with them.
Okay.
And see if there's a class so that I can work on that tomorrow before the weekend and then communicate to you all.
Okay. Okay, Doc.
Yeah.
I'll do so.
Okay, Doc.
Good night.
Okay, good night.